Air movement. Forming wind. Earth is mostly rock or land, with 3/4 of its surface covered by a relatively thin layer of water, the oceans. These two areas strongly influence global wind systems. Uneven heating of Earth's surface by the sun causes some areas to be warmer than others. Recall that warmer air expands, becoming lower in density than colder air. This causes air pressure to be generally lower where air is heated. Wind is the movement of air from an area of high pressure to an area of low pressure. Heated air. Areas of Earth's surface receive different amounts of radiation from the sun because the Earth is curved. Figure 15 illustrates why the equator receives more radiation than areas to the north or south. The heated air at the equator is less dense, so it is displaced by denser, colder air, creating convection currents. This cold, denser air comes from the poles, which receive less radiation from the sun, making air at the poles much cooler. The resulting dense, high-pressure air sinks and moves along Earth's surface. However, dense air sinking as less dense air rises does not explain everything about wind. The Coriolis effect. What would happen if you threw a ball to someone sitting directly across from you on a moving merry-go-round? Would the ball go to your friend? By the time the ball got to the opposite side, your friend would have moved and the ball would appear to have curved. Like the merry-go-round, the rotation of Earth causes moving air and water to appear to turn to the right, north of the equator, and to the left, south of the equator. This is called the Coriolis effect. It is illustrated in Figure 16. The flow of air caused by differences in the amount of solar radiation received on Earth's surface and by the Coriolis effect creates distinct wind patterns on Earth's surface. These wind systems not only influence the weather, they also determine when and where ships and planes travel most efficiently. Global winds. How did Christopher Columbus get from Spain to the Americas? The Nina, the Pinta, and the Santa Maria had no source of power other than the wind in their sails. Early sailors discovered that the wind patterns on Earth helped them navigate the oceans. These wind systems are shown in Figure 17. Sometimes, sailors found little or no wind to move their sailing ships near the equator. It also rained nearly every afternoon. This windless, rainy zone near the equator is called the doldrums. Look again at Figure 17. Near the equator, the sun heats the air and causes it to rise, creating a low pressure and little wind. The rising air then cools, causing rain. Visualizing global winds. The sun's uneven heating of Earth's surface forms giant loops or cells of moving air. The Coriolis effect deflects the surface winds to the west or east, setting up belts of prevailing winds that distribute heat and moisture around the globe. Westerlies. Near 30 degrees north and south latitude, Earth's rotation deflects air from west to east as air moves towards the polar regions. In the United States, the westerlies move weather systems, such as this one along the Oklahoma-Texas border from west to east. Doldrums. Along the equator, heating causes air to expand, creating a zone of low pressure. Cloudy, rainy weather, as shown here, develops almost every afternoon. Trade winds. Air warmed near the equator travels towards the poles, but gradually cools and sinks. As the air flows back towards the low pressure of the doldrums, the Coriolis effect deflects the surface wind to the west. Early sailors in ships like the one above relied on these winds to navigate global trade routes. Polar easterlies. In the polar regions, cold, dense air sinks and moves away from the poles. Earth's rotation deflects this wind from east to west. Surface winds. Air descending to Earth's surface near 30 degrees north and south latitude creates steady winds that blow in tropical regions. These are called trade winds because early sailors used their dependability to establish trade routes. Between 30 degrees and 60 degrees latitude, winds called the prevailing westerlies blow in the opposite direction from the trade winds. Prevailing westerlies are responsible for much of the movement of weather across North America. Polar easterlies are found near the poles. Near the North Pole, easterlies blow from northeast to southwest. Near the South Pole, polar easterlies blow from the southeast to the northwest. Winds in the upper troposphere. Narrow belts of strong winds called jet streams blow near the top of the troposphere. The polar jet stream forms at the boundary of cold, dry polar air to the north and warmer, more moist air to the south, as shown in Figure 18. The jet stream moves faster in the winter because the difference between cold air and warm air is greater. The jet stream helps move storms across the country. Jet pilots take advantage of the jet streams. When flying eastward, planes save time and fuel. Going west, planes fly at a different altitude to avoid the jet streams. Local wind systems. Global wind systems determine the major weather patterns for the entire planet. Smaller wind systems affect local weather. If you live near a large body of water, you're familiar with two such wind systems, sea breezes and land breezes. Sea breezes and land breezes. Convection currents over areas where land meets the sea can cause wind. A sea breeze, shown in Figure 19, is created during the day because solar radiation warms the land more than the water. Air over the land is heated by conduction. This heated air is less dense and has a lower pressure. Cooler, denser air over the water has a higher pressure and flows toward the warmer, less dense air. A convection current results. The wind blows from the sea toward the land. The reverse occurs at night, when the land cools much more rapidly than ocean water. Air over the land becomes cooler than air over the ocean. Cooler, denser air above the land moves over the water, as the warm air over the water rises. Movement of air towards the water from the land is called a land breeze.